Today's video is going to be about linearization, and it turns out that's the same thing as just finding the tangent line and using it as an approximation. So let's look at four graphs here. This is a quadratic, this could be some sine or cosine, this could be some exponential looking thing, and this could be some square root function, okay? All of these things are more complicated than just some linear function. And so what we're going to do when we do a linearization is that we're going to use a tangent line as the model. Okay, so instead of looking at a quadratic, what if we were only interested in points around that red dot? Well, if we looked at the tangent line and you zoom in there, the tangent line and the curve itself are super similar around that point. And again, at that point, they have the exact same y value and the exact same slope. But even in the points near it, if we linearize this quadratic and we're only looking around there, the tangent line is a really good approximation or model for the curve. If we look at a sine curve, and let's say we look at that dot and we can find the tangent line, it's going to look something like that. We look at an exponential, we look at the tangent line at that point. It's going to be something like that. Again, all of these linearizations are just turning the curve into a line, specifically the tangent line, because the tangent line has the same slope and y value as the function does at that point, and then we can use that. We can look at the tangent line right there. And again, at those points, the tangent line is really close. The one thing I don't like about what textbooks do is they give things new names, like linearization, and they give it a new formula, and they act like it's something different than what we've already done. If you looked it up in some textbooks, they're going to say the linearization formula, L of x, is equal to, right, they're telling you how to find this linearization, f of a plus f prime of a times x minus a. Right? They're going to tell you this new formula, and they give you this new letter, L of x, representing this line. And I kind of just think that's ridiculous. This is the same thing as Algebra 1. We know how to find the equation of a line. All you need to know is a point and the slope. This point-slope equation, knowing m and knowing x1 and y1, is the exact same. Hopefully you can see that these match up perfectly. M, well, what is m? Well, it's f prime at a. X minus a instead of x minus x1, and then this, instead of minus y1 on the left side, you could just add it over here and get f of a. Right? What is f of a? It's the function's value at a. That's what y1 is. So please don't view this blue as some new found formula. I mean, all they're going to say is find the tangent line, use it to approximate the curve, which is what linearization is all about. Okay, so I'm going to do 4 examples, but linearization is really just a repeat of what we've already done in calculus. We're finding a tangent line, we're using that tangent line to make an approximation about the curve, because the tangent line is just an easier function to analyze than a quadratic or a sine or an exponential or a square root. Lines are just easy. So let's start out with y equals x squared plus 4, and let's find the tangent line at x equals 1. So we need to find y prime, which is then 2x. We can identify the y value at 1, what that's equal to 5. The slope, y prime, at 1 is 2. And then we can use point slope. Y minus the y value equals the slope times x minus x1. And we can solve, and we get 2x minus 2 plus 5, and that gives us plus 3. Okay, this is the tangent line. This is the linearization of this quadratic. If you drew a picture of this quadratic has a y-intercept of 4, and so generally it kind of has some shape like that. The linearization, this line right here, is the tangent line at 1. It looks something, oh, I don't know, like that. Okay, that's the red. And the red, the linearization, is really close to the quadratic, centered around x equals 1. Okay, we could do a sine curve. How about y equals sine x? Let's do the linearization at x equals 0. So to do that, we need to know the derivative, which is cosine x. The y value, well, sine of 0 is 0. The derivative, cosine of 0 is 1. And so then we're doing y minus 0 equals 1 times x minus 0. And we get the linearization that y equals x. Okay? All right, that's the linearization of this trig function at 0. So there's sine x. And if you look at the linearization, y equals x is our linearization. And you likely already used the fact that sine x and x are super similar when x is equal to 0 previously, right? We already looked at this and used this way back when you looked at the limit of sine x over x as x goes to 0. You remember that limit? It's equal to 1. We'll look at the two functions. Sine x and x. X is the linearization of sine x. And so when x is equal to 0, well, those two things are the same function, so their ratio equals 1. Okay? We use this in physics. If you end up in a physics class, so kind of a side note, if you're not in physics, you're never going to take physics, you can just close your eyes here. But eventually, we're going to look at a pendulum swinging back and forth, and we want to look at the period, meaning the time it takes. Well, it's going to turn out that that's going to have a trig function in it, but we're going to use the fact that sine x is super similar to x. So in here, we're going to say that sine x is pretty much x as long as x is small. And really what we're doing is we're using the linearization. And again, you can look at that, but it's the small angle approximation. Okay, so back to calculus. Let's do an exponential. Y equals e to the x. And let's do this at x equals 0. So y prime, well, the nice thing, the derivative of e to the x is e to the x. And so y, when x is 0, y is equal to e to the 0, which is 1. And y prime is also 1. So then y minus 1 equals 1 times x minus 0. And you just get the curve x plus 1. When you think about this exponentials, exponentials look like that. This is the point 0, 1, and we're finding the tangent line there. So it's got a slope of 1. So something similar to that. That would be the linearization. Okay, and again, what if, how could we use this? What's an application? So here's our application. What if we wanted to approximate this function when x equals 1.2? Well, I don't have my calculator on me, so what is that? I don't know. I know what the real answer is. The real answer is e to the 1.2, but I don't know what that is. I have no idea what e to the 1.2 power is, but I can use the tangent line to approximate it, because this linearization, right, L of x equals x plus 1 is the approximation for this curve. Well, we'll just plug in x into this then to approximate this. And so this would then tell us that L of 1.2 is just plugging 1.2 into here. So this is 2.2. And so what we're claiming is that these two things are similar. If they are not exact, this is the tangent line approximation for e to the 1.2, because I'm just plugging in 1.2 into that. The further you get away from the tangent line, the worse it's going to be. So I moved all the way to 1.2. Okay? I centered this tangent line at 0. So at 0, they agree, right? E to the 0 is 1. 0 plus 1 is 1. They're perfect matches at this, right? That's where the approximation or the model starts. If you move away, it's going to get worse. And you can check to see that that's not a great approximation, right? It's an underestimate. This curve is going to zoom away. And this tangent line is going to be an underestimate. But at least it is an estimate. And if you want to get better with it, just don't go as far as I did. For 1.2, try something like, I don't know, e to the 0.5. Okay, bust that up on your calculator. Don't have it in front of me, doesn't matter. An approximation for that is just plugging in 0.5 here. I bet it's something close to 1.5. And again, you can verify that on your own. Okay, so what we do here, and again, we could do one more quick function if you want. We could look at the square root. Square roots are also hard to do, and sometimes it's nice. Let's look at the square root at, I don't know, x equals 4. So the derivative, the power rule, bring down the half, decrease the power by 1. So the derivative is 1 over 2 radical x. Y is, well, y is the square root of 4, so that's 2. Y prime is plugging in 4 here and getting 1 over 2 radical 4, which is just 1 over 2 times 2, which is 1/4. And so our linearization ends up being 1/4 x plus 1. I kind of skipped the step of writing it because I'm running out of room. But again, if I wanted to approximate, what's the square root of 5? Well, just use the tangent line. Use the linearization. L of 5 is plugging in 5 here, and I get 5/4 plus 1, so that's 1.25. So I'm guessing that's 2.25 is approximately then the square root of 5. This linearization is the tangent line that approximately gives us a model for the square root. Again, it would look something like, there's the square root. At 4, we're looking at the tangent line, and we're using the tangent line's value at 5 instead of the square root of 5. But I'm claiming that they're pretty similar. Again, plug in the square root of 5 and you're going to get something close to 2.25. Again, linearization is just finding tangent lines. Why are we doing this? Because we're using the tangent line for an approximation. Why? Well, because there are going to be times where instead of trig functions, we want lines. Instead of exponentials or square roots, we want lines. Or we want a quick estimate on e to some random power or the square root of something we don't know. Well, we can just use the tangent line to accomplish that.